All right, any questions on the assignment from yesterday? Felix,
Go number 6.
on the back?
Yes, sir.
Okay. So visualize this, right? I've got this rubber stopper swinging around over the top of my head, right? Now, clearly, the faster it's going to go, what happens to the distance it's going to travel? Right? It's going to go further, right? The faster it's going, the further it's going to go. But is the rate at which I'm spinning it going to affect the amount of time it takes for it to hit the ground? In other words, if I'm spinning something pretty slowly, okay, and Shively's spinning something going much, much faster, and we both let go of them at the same time. Same height. Shively lets go of his is going much faster. Mine's going much slower because I'm older, okay? He's youngster, he can handle it. I'm old. But which one's going to hit the ground first? Same time, because what's the only thing that determines how long it takes for something to hit the ground? The initial vertical velocity, which is going to be what? 0, because they're spinning it around horizontally. What else? Gravitational acceleration and what? No. Let me give you a hint. Rhymes with distance. Distance, right? How far it has to fall. So you're spinning it around up here like this. And it's, what is it, 1 point?
You have an appointment at 3:30. I'm going to send you the contact information.
Beautiful, thank you.
If it's a chiropractic appointment, let me know.
Well, I didn't realize I could schedule appointments with her.
Huh?
I didn't realize I could schedule appointments with her.
Well, not with her.
I know. No. Well, she'll take care of my dentistry.
Okay, so here's the deal. If I drop the stopper from 1.8 meters, which is about like yay, or I spin it around and let it go out horizontal, is it still going to take the same amount of time? Yes. And you know that distance equals 1/2 AT squared plus V naught time. True? Is this the velocity of the stopper, or is that 0? Why is it 0? Logan?
Because the vertical velocity is 0.
Yeah, I'm spinning it around in a horizontal circle. That's 0. Do you know how far it falls? Yeah. Do you know your gravitational acceleration? Yep. Can you find the time? Okay, because if your answer to 6A is wrong, everything else is going to be wrong. So your answer to 6A should be around 0.6 seconds. Okay? Now, then I want to know, on that one, what's the velocity of the ball? This is before, what's this while still attached to the string? Okay? Well, it's still attached to the string. So you know how long it was in the air, right? So at this point, you know, oh, it's going to come out like this, right? So you know how far it travels, and you know it takes about 0.6 seconds. And then you go, oh, range equals Vx time. So this velocity is how fast it was going while it was still attached to the string. Then once you get that, and so if all goes well, your answer to 6C should be something around your current age. Okay? Everybody cool with that one? Huh?
You were right. Not even wrong.
Or who was it? Yeah. Okay. All right.
That's interesting.
Anything else? Yes?
So, what's the direction on number 4?
Okay. Vonda. Is this thing...
Just got to pack up.
Is number 4 about the discus?
Yeah.
Yeah.
Okay. So imagine this is the discus, right? So this is what's going to be happening, right? So when I'm going around like this, what does the discus want to do? Does it want to travel in a circle?
No.
What does it want to do?
Go straight.
It wants to go in a straight line. I'm making it go in a circle, right? So what's the direction from my hand? It's either going to be, the force from my hand is either going to be directed outward or it's going to be directed inward.
Inward.
and at
90 degrees.
to the,
Tangent line?
nope, rhymes with velocity vector.
Velocity vector.
There you go. Anytime I ask you the direction of any centripetal force, do not pass go, do not collect $200, do not think. Any force on a centripetal motion is directed inwards and at right angles to your instantaneous velocity vector. Always, always, always. This is why it's called centripetal force, because it's from the Greek word meaning inward seeking. Okay? So there's your lesson in ancient Greek. Now, make sure, please, 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 on the front page, every one of your answers has 4 significant digits, okay? And let's say, for example, your answer to 1J,
3 significant digits.
huh?
3 significant
Three
digits.
significant- What did I say?
4.
3. That's what I meant. Somebody asked about it. You know what I meant. So, I just saw 4 because this is where I was going. If on 1J you have this answer as your coefficient of static friction, or your coefficient of friction, how many significant digits does that have?
1.
1. How many do you need?
3.
Now, here's what you can't do. Just don't go and chalk zeros on the end of it, okay? If you have this as an answer, it is not acceptable. You need to go back and recalculate what you did to get me more digits out this way. Because if you just write .004, these zeros are freshmen. They are taking up space. I don't like them. They don't count. Okay? Or you can put it in scientific notation. That's even better. That way I don't have to count freshmen. Okay. Anything else? Michael?
Is the force for number 4 supposed to be a really big number?
It should, the force for, your answer to number 4 should be around 500,
Okay.
give or take, a little bit, maybe 1. Okay. Anything else? Going once? Now let me talk about, let me talk about your answer on 1L, make sure everybody's cool with that. So here's the deal. So here's Al, right, and here's the green spinning thing. So as he's going to walk out towards the edge of the green spinning thing, assuming that it's spinning, okay? That's why it's called the green spinning thing. Here's what you want to look at. Is that centripetal force equals mass 4 pi squared r over t squared. As Al moves further and further and further to the outside of the edge, what happens to the value of t? Nothing. It stays the exact same because no matter where Al is, it's going to take the same amount of time to go around that circle. So t is going to stay the same. Is his mass going to stay the same?
Yes.
Yeah. So basically this whole thing becomes a constant. Okay, as Al is walking towards the outside. This whole numeric value is just a constant. So since this is a constant, you can simplify this as saying, oh, that's just some constant times radius. So as your radius gets bigger, what happens to your centripetal force? There you go. That's how you want to approach that last question. Okay? Anything else? Going once, going twice, sold?
No points though.
All right.
Only pancakes.
So here's going to be the whole purpose of this lab, and this is why it's become known as like the cowboy-cowgirl lab, is that what you do is you take a rubber stopper swung that has a rubber stopper tied to the end of it, the string tied with a rubber stopper on the end of it. It's going to go through a glass tube, and the end of the tube you're going to have, in this case, like a 200-gram mass. So what you can do then is get it spinning, and then the 200-gram mass will just stay there. Now, if I go a little bit faster, okay,
We do.
hold on, or if I slow it down,
Brandon, how did
That's crazy.
okay? So I have the capacity to change the radius, right? Or go a little bit faster.
That's how helicopters work.
Doesn't that make sense? That should be the new helicopter right there.
One rubber stopper on the end of the string. Don't expect me to
Okay,
invest.
but how is it going
Okay.
to move?
It's moving right now. He's saying.
But the
that
rubber stopper
to pick it
down.
up. The rubber stopper is the propeller,
Blade.
and then the body itself.
So
is
the
is
helicopter
weight.
crunches up.
Yes.
Okay.
Yes. Isn't that
That's realistic.
Isn't that
Everyone inside
realistic?
can just die.
All right. So,
Bro, you're solid. You could use an elevator like that, right?
They're the
Yeah,
slabs
you could.
for cowboys and cowgirls. They're the ones
Okay.
that need it.
Who? Them?
Them.
Get him. Get him. Dang, Maddie. Ice. Ice in her veins.
okay. So here's the question. As this thing is going around, okay, right, like this,
Yeah.
what are some things that I can measure?
The time for it to take one revolution.
Okay? Now, so it's going to be tough to measure just time for one revolution and get a precise measurement. So what could we do instead of just trying to measure one?
Average
Measure
or
five.
multiple.
Well,
Measure 5.
well, more than 5. Let's do something simpler. 10. Okay? So let's measure the time for 10 revolutions. So why do you think, why would it be easier to measure 10?
You can just move it a decimal.
Yeah, then you just have to move a decimal place, okay, to get the time for one. So what you're going to do is you're going to get, who's ever going to do the swinging, okay, you're going to get this going, and then you're going to have at least 2 people counting. Now, in the name of lab protocol, okay, don't do this. If you're one of the people counting, don't do this. 1, 2, 3. Okay, if you count out loud, people are going to want to beat you with a stick, okay? And I'll probably let them. Because you all are in honors physics classes. We know you can count to 10. You don't need to show off, okay? Now, you can look like a guppy starving for air and go,
It's about to hit your head. Be
okay?
careful.
Okay. So, I don't care how you count it. Just make sure that you're not counting out loud. So Cale Eckert actually developed a new technique, and it actually worked fairly well. He actually ended up laying on the ground and counting it as it went by over his head.
Kale
Okay?
Eckert. Kale Eckert.
Yeah, it is Cale, right? It's the Cale count.
Let's go, Kale.
Because here's what goes south with this lab. The lab is a home run. Ironically, what you screw up is the ability to count 10 revolutions and get the time. Okay, literally, that's where things go south. So, this is why you want to have 2 people timing. So if you have 2 people timing and you're off by like 2/10, probably somebody can't count to 10. Okay, either somebody counted 11, somebody counted 9, something like that. So this is why you want to have at least 2 people counting. So if you're off by like quite a bit, it's because somebody didn't count the 10 revolutions. They counted 9, they counted 11, something like that. So if you're off, don't just take the average, okay? Somebody didn't count to 10, because the time should be pretty similar. Okay. So we can measure the time, okay? We're going to measure 10, we're going to divide by 10, move the decimal place, boom, we're off to the races. So we got that. What else can we measure? Radius. Now, the radius gets a little dodgy, okay? Mainly because if this thing is swinging around over your head, okay, it's going to be tough to measure the radius on a swinging object, okay? You can do it, but probably somebody's going to lose an eye, and it's just going to be awkward. So what you want to do is lay it out like on the ground. You want to measure from the center of the mass of the stopper to the edge of the tube. So let's say like on the first 4 trials, you want to have a radius of 0.7 meters. So you want to lay this thing out from the edge, from the middle of the stopper to the edge of the tube, make that 0.7 meters. So then what you can do is take like a magic marker or a Sharpie and make a mark on the string. Because then, and you don't want to make that mark on the top, okay? Because it's going to be tough to see the top of that rubber stop of that tube because it's going to be swinging around over your head. So You want the bottom, make a mark here. So one option is that you make a mark. You can also take like a small piece of tape and put a small piece of tape on the bottom. That's an option. If you like paper clips, I can give you a small paper clip and you can put a small paper clip there. I don't care, okay? But just have some way of visualizing so that when when that mark hits the bottom of that tube, you know that way you're at a 0.7 meter radius or whatever you want that radius to be, okay? So we can measure the radius, we can measure period. What else do you think we ought to measure? We got to, that's wrapped up in the period. What else can we measure? Of what?
Stopper.
Mass of the stopper. Okay, that's pretty simple. I'm going to have an electronic balance back there. Don't try and measure it with a Newton scale. You won't get a good enough reading, okay? So I've got an electronic balance back there. Take your rubber stopper, put it on there, boom, there you go. Now, here's the other thing that we're going to assume. What's the role of this 0.2 kilogram mass down here?
Making opposing force.
Yeah, because if I'm swinging this thing around, okay, we won't do this, but if I'm swinging this thing around and get this thing going, and then Bree comes along with a pair of scissors and she cuts this string. If she cuts this string, what's going to happen?
It's going to fly off
It's going to go fly off. Why?
because there's no force holding it in.
Exactly. There's nothing providing the inward force. So the purpose of gravity acting on this 0.2 kilogram mass is to produce the inward force to keep this thing moving in a circle. So what we're going to assume initially is that whatever the weight is of what's ever suspended from the bottom, not the mass of the stopper, okay, not the stopper mass, this, whatever the weight of this is what's creating the centripetal force. So when you get down here to trial 2, where it says 0.2 kilograms, okay? So you got 0.2 kilograms, so what's 0.2 times 9.8 meters per second squared?
1.96.
1.96 newtons. So like on that second trial, if I were doing this, and I had a 0.2 kilogram mass, under this column where it says centripetal force, that's going to be the weight of whatever the mass that's hanging down is equal to. So if on that 0.2 kilogram mass, I'm going to come over here and I'm going to write 1.96 newtons. If it's 0.1 kilograms, the first trial, what's that weight going to be?
0.98.
0.98, so that's going to be 0.98 as your centripetal force. So your centripetal force is going to be whatever the weight is of the hanging mass. Okay, that's the initial assumption that we're going to make. Because this, what we're going to say is that this is providing an inward force of 1.96 newtons. So, here's the mother of this whole idea. Is that it's mv squared over r. Okay, this is the equation that we came up with yesterday. So here's the million-dollar question. Is this mass the mass of the stopper or the mass of what's hanging down below? Hanging? Stopper. Stopper, because why? You're right, that's the mass of the stopper. Why is that the mass of the stopper?
Because the mass is making the outward
Yeah,
force.
'cause that's what's going around in a circle, right? Felix just went this, right? Yeah, because that's what's going around in the circle. So this is going to be the mass of the stopper. Here's your radius, here's your velocity. Now, here's what you've got to be able to do with a complex equation like this. We basically have 3 variables that we can manipulate. We can change the amount of centripetal force, that's what's going to happen on the first 4 trials. So this is the value that we're going to alter. We're going to keep the mass of the stopper the same, and we're going to keep the radius the same. So basically, this part of the equation, this ratio of mass to radius, is going to remain a fixed value. Okay, that's it. This is just going to be some number. Depends, and it's not going to be the same for everybody because you're going to have different size stoppers. Okay, but within the first 4 trials, this value right here is just going to become a constant value. That's it. Some mass to radius ratio. So think this through. This is going to be some number. I don't know what it is. I don't care what it is. Not right now. I don't care. But what it's going to simplify to is the centripetal force is going to be some constant times b squared. Now, if you're in a math class, and I said, hey, class, we're going to graph y equals kx squared, what is y equals kx squared going to look like?
Probably.
Parabolic curve, right? It's going to go something like this. True? Y'all have graphed this before, right? That's what you got. So since this is y equals kx squared, so we're going to graph centripetal force versus velocity. Okay, and this is what we're going to look at. This is what we're going to see. So here's the deal. If you look at what's going to happen on trials 1 through 4, this number here is going to stay the same. This ratio of mass to radius is going to stay the same. But I'm going to make the centripetal force bigger. So if I make the centripetal force bigger, what has to happen to the velocity? It has to increase, right? Because I got to keep two sides equal. So to generate more and more centripetal force, I've got to make the stopper go faster and faster. Okay? Now, so more centripetal force, as long as mass and radius are constant, I've got to make the stopper go faster. Now, this is where you take it to the next level in terms of an analysis. Well, how are you going to calculate the velocity of that stopper? What two things do you need? What two things do you need to know to calculate the velocity of that stopper as it's going around? What are the two things you need to know? The radius, which is going to get you the circumference, and the time. So this velocity is going to be 2 pi r over t. Well, in the first 4 trials, are you going to change the circumference? No, that's going to remain constant because we're not going to change the radius. So what's the only way that I can create a bigger velocity out of this equation? What has to happen to the value of t? It's going to become smaller, right? So when you go through trials 1 through 4, what you should see with the period is that the period should get smaller because the rubber stopper should be going faster to create more and more and more centripetal force. Okay? So if you look at your analysis, you can kind of figure out ahead of time, wow, what should be happening as I look at this data? All right. Now, this is why it's so important that you have that mark where you can consistently produce that same radius. Make sure that your rubber stopper is tied on. I don't want this thing turning into a projectile lab. Okay? Would be cool. Not really going to happen. Okay? So make sure that's tied on. Make sure that you've got your weights secured. Now, what I would recommend on trials 1 through 4, I'd recommend that you kind of choose like a medium-sized stopper. I've got some really big ones and I've got some really small ones. I kind of choose a medium-sized stopper. I would actually I'd reverse the sequence that you have there. I'd actually do the 0.4 kilograms first. And here's the reason why. Because if you choose too small a stopper, this mass becomes a really small number, so your velocity has to be really, really fast. So sometimes it can be going so fast that you really can't measure or get a precise measurement on the period. So what I would recommend is that I'd actually start with 0.4 kilograms and then work your way back up. So I'd start with the most difficult one, which is going to be the 0.4 kilograms, because that's the one that has to be going fastest. Because what I don't want you to do is get down to the 0.4 kilogram mass and realize, wow, this thing is going so fast, we don't have a chance of getting precise data. Okay? So that's why I'd start with that 0.4 kilograms and then work your way back up. Okay? Because if you can do the 0.4, the other ones are going to be simpler to do. Make sure that when you're doing this, this thing is going in a horizontal plane. Okay? I don't want it like some tilted helicopter thing going, trying to fly through the air this way. Okay? I want a straight lifting, so I want a straight, pretty flat horizontal plane as this thing's going around. For those of you that are going to be doing the swinging, here's your technique. Okay? I'd hold on to the bottom, just hold on to this, okay, and get it going, and then you'll actually feel it when it's going fast enough, and you'll feel it take that tension off. And I'd kind of keep my hand around like the string or something to keep this thing from like swinging back and forth, okay? Then that throws a whole another element into this data. So I just kind of keep your hand like this, okay, and try and keep everything as steady as possible. So just hold it, and you'll feel it once you're going fast enough, because you'll feel it kind of start to lift up off that tension. Okay? Now, that's trials 1 through 4. On trials 5 through 8, I want to keep the centripetal force constant, and I want to keep the mass of the rubber stopper constant, but then I want to alter the radius. So here's what you want to look at on that one. So on 5 through 8, you're going to go centripetal force equals mv squared over r. So let's kind of figure out what we should see. I'm going to keep the mass of the rubber constant. This mass of the rubber stopper is going to remain a constant value. It's not going to change. I'm going to keep the centripetal force a constant as well. Okay? So if you wanted to, you could move this mass over here and go, oh, that's centripetal force over mass equals v squared over r. Now, you don't have to. But what you could look at is say, okay, hey, this whole thing becomes a constant, because I'm not going to change the amount of centripetal force. I'm going to keep that the same. I would recommend on trials 5 through 8, and I don't care which one you pick, but I'd either have the 200 grams or the 300 grams as creating that centripetal force. 100 grams is pretty small, and that's going to be tough to do. Okay, so on trials 5 through 8, I'd recommend either using the 200 or the 300. I don't care, but I'd pick one of those two. Now, here's the beauty of trials 5 through 8 is you're going to be changing the radius. If you want to, you could actually use one of your trials for 1 through 4 as one of your data sets on trials 5 through 8, because as long as you use the same centripetal force and the same radius, you can count that as one of your data points in the next set of trials. Now, it's interesting, if you want to make sure that you did it right, try that same data set again and see if you get the same values. If you try it like a second time and go, okay, let's see if we can recreate what we had before. So here's the point. This whole thing is going to be a constant. So as the radius gets bigger, what has to happen to the velocity?
It's gonna have to be big.
It has to get bigger because I have to produce the same number over here, right? But is it going to increase in a 1-to-1 ratio? Why not? Because this one's squared, okay? Now, if it was just v over r, then they'd have to change in a 1-to-1 ratio. So if you double the radius, you double the velocity. But this number is going to be squared, okay? So what you should see as the radius gets bigger, you should see the velocity getting bigger as well, but just not at the same ratio. So on 5 through 8, when you change those numbers, I'd recommend that you change at least 10 to 15 centimeters in between each trial, okay? At least 10 to 15. Don't go like, 70 and then 71, 72, 73. That's going to be such a small change in radius that you're not really going to be able to see a trend. So you want a pretty big gap in the radii in trials 5 through 8. Like I said, you don't have to use 70 centimeters as one of your data points. If you don't like that, hey, fine. You don't have to use it. But again, I'd have you want at least 10 or 15. So what you could do is go like 100 centimeters and then go to like 85 and then to 70 and then like 55 or something like that, okay? But just get, the bigger the gap is in that radii, the better you're going to be. Don't try and make that radius smaller than about 0.3. 0.3 even then is pretty tough to get some good data on. So don't get too small on your radius or it's going to be hard to count. So here's what you're going to do. This first block was all screwed up because of the senior pictures and all that good jazz. So here's what I want everybody, my two classes to end up at the same point. So today I want you to get through trials 1 through 8, okay? We'll do 9 through 12 on Monday, right? So just get through trials 1 through 8. But take your time, look at your data. Don't be afraid to go back and redo the data set if it doesn't look like it's fitting in with the trend. So you got a bunch of calculations that you do. You need to calculate the velocity, the period, all this good stuff. Down below, I don't want to see all 12 trials. I just want to see your calculations for trial 1. Okay, that's all I want to see. I don't want to see them clearly written out. Okay, I just want to see them for trial 1. That's it. I don't wanna see the other 11, but I do wanna see trial 1. Okay, then if you want to get aggressive, over here on page 2, you're gonna have to graph some stuff. In trials 1 through 4, you're gonna plot velocity on the x-axis and centrifugal force on the y-axis. And then on 5 through 8, you're gonna do radii on the x-axis and velocity on the y-axis. Those graphs are gonna start at 0, 0. So when you set those up, when you do those graphs, don't change the scale, okay? So whatever you start with, like if you let 2 squares be 0.1, I don't care what it is, but you have to keep the same thing going across. And if you go up and let each one be 1 Newton, okay, fine. I don't care how you set it up, but some of you have this annoying habit of setting up a scale and then you change it later on, okay? I don't care how you set up your scale, but you have to be consistent on how you set those up, okay? All right, so you really don't have any homework, but I at least want you to get through trials 1 through 8. When y'all get done, the tubes are in a box by the rubber stoppers. When you get done, dismantle everything, put the string back, put the meter sticks back, throw away the string that you got.